Thank you very much, Siet. After this talk, coming down to earth is not easy, I must say, but I will try. I also start with planet Earth. Siet, you talked about Top of Europe, which is an important initiative also in the aspects I will explain and detail now. Well, when we talk about our planet, we talk about the geosphere, we talk about, of course, solid Earth, the lithosphere, we talk about hydrosphere, water was just mentioned very intensively, but also the atmosphere, the biosphere, and what we call the critical zone, the pedosphere. And in this context, we have to see that we have quite a number of challenges, and I will have one example, which is maybe one of the most important and demanding challenges, climate change. We have seen from the previous talks that natural factors are important, but also man is influencing climate with its activities, particularly related to using resources, particularly fossil fuels. And when we look into a little bit into the development, planet Earth and climate, we can go back, and this was also in the previous talk, maybe 600 million years ago, where life developed dramatically, first in water, in the oceans, and then also on land. And what you should see is simply these four stripes, one stripe situation in pink and one in blue, and we, from the geological point of view, we call it the greenhouse and the ice house. And why we had these dramatic changes where we had ice on our planet or practically no ice on our planet, there's a number of ideas and speculations, but not really profound knowledge or systematic knowledge to explain this. It becomes clearer when we look into the more recent development into the time window 2, where we have this ice house situation, where we have ice on our planet in the higher elevations of the mountains and, of course, in the Arctic and Arctic regions. And there you see, when you look into specific parameters that are relevant for climate, you see an up and down. So we have, as we know, cold and warm phases, even under these conditions. And these can be explained by the so-called Earth parameters, the Earth circling around the Sun in an elliptic format. The axis is not stable, it's shaking, and a number of other processes are really, related to these kind of developments. For us humans, it is, of course, of interest to understand these dynamic situations and to see, for instance, when was the last warm period, which is about 130, 140,000 years ago, the aim. And then we had a period of 120,000 years of cold with high variability, and 10, 12,000 years ago it became warm again in a very more or less stable situation. So that's where we live right now as our societies and human beings. Now, what's new? Why is man having an impact and is becoming a geofactor, as we might say? Is this dramatic changes in the atmosphere, what is called the so-called greenhouse gases, so radiation that is coming into our system is not reflected in the same order of magnitude, and this causes this global warming effect that we actually see. And when we look into specific parameters obtained from ice cores, for instance, we see that over a certain period of maybe 800,000 years, 1 million years, the CO2 concentration in the atmosphere had not reached levels above 300 ppm, and we are now reaching about 430 ppm, and since maybe the 1950s, 1970s, this cannot be explained by natural dynamics. It can only be explained by the impact of man, particularly using burning fossil fuels, but also by land management processes. And also the rather steep and fast development of the CO2 concentration in the atmosphere is seen or is discussed to being a new effect. So these impacts have clear effects on our life, on the way we can act, how we can treat the planet for our survival. One aspect is, for instance, that the changes that are related to this climate impact, this anthropogenic impact by man on the climate, is that, for instance, the Arctic has warmed faster than we expected compared to the more continental regions. This is not only causing faster melting of the ice in the Arctic, but also has an impact on the jet streams about 10,000 kilometers above the surface. And this is impacting the weather situation and causing more extreme weather patterns, longer dry periods, and maybe also precipitation regimes are changed due to this situation. So it's a complex system, and we have to understand planet Earth in an integrative manner, also with these more short-term effects. Now, when we look into the country I come from Germany, over the last 100 years, from our National Weather Institutes, Deutsche Wetterdienst, you see that even in a small country like Germany, over the last 100 years, things have changed as compared to temperature and precipitation regimes. And interestingly enough, and of course this is related to the geographic situation, we have a higher warming situation in western part of Germany as compared to the east. And this is also related to precipitation. So we have, particularly in the mountainous regions, we have higher precipitation over the last 100 years, up to 100, even 200 millimeters per year precipitation, whereas in the east we have the opposite development. So we have these regional developments, these regional impacts of this global climate change effects, and that means, for instance, in eastern Germany, we have now a little bit less precipitation, but particularly changes in the pattern. So it's you have more precipitation, rainfall during the winter period and less during the summer period. And during the summer, it has changed from a more continuous type of precipitation to intensive precipitation events. And so that was the last 100 years. And when you look into this more actual development, we can see that we have a very clear effect on this impact of higher temperatures, extreme drought events, particularly in the east, higher water storage in the atmosphere, more evaporation, heavy rainfalls, as I mentioned, and lower water infiltration capacity with regard to groundwater formation. So soils come into the play when you try to understand these impacts as the living part of the uppermost part of the Earth's crust, again, the pedosphere, and soils interact with the lithosphere, the hydrosphere, the atmosphere, biosphere, and with the technosphere. When you look in the technosphere, the mass of the technosphere is now equal of the mass of the biosphere. So we have dramatically changed the surface of our planet. So some of us call it the Anthropocene, starting in the mid-1950s, what we call the great acceleration, human population, demand of resources, building structures, infrastructures, and so forth. And humans have become a geofactor. And one example is that I have shown is the impact of man on climate and the anthropogenic impact of the actual climate change that we are seeing today. Now, soils as the living part of the upper part of the crust is of course not by itself. It's interacting also into the deeper lithosphere, and this is important to understand. First of all, in terms of the geological parent material for the development of soils, but also, of course, the hydrosphere and the biosphere, and man, I will show this at the end, plays an important role. Now, when we talk about the hydrosphere, water, just a quick overlook. Most of the water is in saline water. 70% is covered by water of our planet, of the oceans. We have only less than 3% is fresh water, and thereof only 30% is groundwater. And groundwater is an important resource for human life, for human activities. And as mentioned before, here there is a lot of water in our planet. I mentioned it here as well. In this sphere, 400 to 660 kilometers, in different minerals, probably the same amount as in all the oceans. So that's amazing, and there are discussions, but really we don't know where all the water is coming from on our planet Earth. Well, now, what does it mean for the surface, for the soil situation? You have precipitation, and that falls on the surface. It may fall on the, of course, on the biosphere, but also directly on the soils and agricultural activities, whatever. And you have runoff, you have drainage water to go down for groundwater formation. You may have uptake in the biosphere, and then you have transpiration, and water that is falling on the biosphere may also evaporate, so we call it evapotranspiration. And you have different processes, of course, in the soil related to the percolation, the infiltration of water down to the saturated zone. And to show that these processes are maybe not as well understood as our modeling approaches might give us the idea, we built for the first time an artificial watershed when I was at the university in Cottbus, where we have these huge open cast mining regions, and we could actually extract geomaterial that was deposited there right after the Ice Age. So that is the situation after the Ice Age. We built this watershed, and we measured all relevant parameters: precipitation, percolation, evaporation, transpiration, whatever, runoff, and so forth. And we invited, together with, this was a big project together with the ETH Zurich and the Technical University of Munich, and our colleagues from the ETH, Hannes Flüler, we invited together the leading hydrological modelers, and 9 of the 10 invited came, and they all could run their models on this for the first time really measured situation for hydrological parameters. And as a result, we found that practically all hydrological models underestimated the surface runoff. As a consequence, we might have much less groundwater than we would assume. And this, of course, is related to processes that are relevant for soil. So we call this an important process with erosion or runoff is the hydrophobicity after specific conditions. So when soils dry out, they may also build up biological crusts, and that would then stop or really decrease the amount of water that can, when you have precipitation, that can infiltrate, percolate into the soil and form groundwater for many purposes, and you have much more erosion. So that was one insight, and this is actually an important factor with climate change, where you might have longer dry periods and heavy rainfall events with thunderstorms. So it does not only cause less groundwater formation, but it will also cause more erosion, and fertile soil might be transported out of the landscape into rivers, into sedimentation processes. Another aspect is with dry situation that you might interfere with the capillary rise of water vapor from the saturated zone in the soil to the unsaturated zone, which is very important again for the water supply for biomass. And one effect, for instance, in our situation in Germany is a large decline of forest land to the fact that in Germany the forests are not a CO2 sink anymore, but a CO2 source, officially nominated now. So you see these interactions, to understand these interactions are really, really important. Maybe not on the galaxy and long-term period, but for us human beings living today and in the future with the effects of climate change. Another aspect is, of course, what do we do with the soil? As I can only show this, I only show this impact here directly, is that we use it for agricultural purposes. Of course, we want to produce food, biomass, and so forth. And with that, we use heavy machines and heavy machinery, and that causes an impact on soil compaction. So we might plow the upper part of the soil, but the deeper soil, down to a depth of maybe 30, 50 centimeters, it's compacted. So again, when you have rainfall now under these conditions, and even if some water might penetrate into the soil, it cannot penetrate deeper. And then you have these flooding situations that we experience already in large extent. So there is a number of aspects that has to be, yes, as a consequence, in dry years, there is a lack of water in the topsoil and water logging after heavy rainfall events and huge flooding effects. And when you understand this situation, there is just a paper by Greenwood in Science showing that the estimate for the number of people in the world without safe drinking water, and this is the groundwater situation. Of course, there's some desalination with ocean water, but this is really the most important aspect. Safe drinking water, up from 2 billion to 4 billion people. So, and this is already the actual situation, and we must assume that this situation becomes even more severe with the impact of climate change and the effects of drought and waterlogging, but also the way we use soils for different management purposes. So, there is no sustainable production as such without soil and without knowledge. You know, the famous production factors: soil, work, capital, knowledge. So we need soil knowledge. And what does it mean? What are the aspects of soil? It's, of course, the mineral components. That's often overlooked. The geological parent material is really very, very important to understand the dynamics and the processes in the soil. Of course, we have then water, we have air, and we have plants, animals, plants that grow in the soil, and they form organic matter, humus. And this is extremely important for carbon storage, for water storage, and of course as a habitat, as an ecosystem for, and the source of nutrients for plants and soil organisms. So the central relevance of soils for humans means biomass production as one aspect, for food, for fiber, for energy. But also in terms of biodiversity, this continuum of soil biodiversity, of living soils, and the above ground biodiversity. Water I have just mentioned. CO2 sink, carbon storage, georesources, for building and other geological resources we need, as a fundament, as an underground to build something on for infrastructure and so forth, but also as a landscape element, as an ecosystem compartment, and as an archaeological monument. So another thing, despite the hydrological aspects I have mentioned, is actually the biodiversity situation, the ecosystem continuum. There is no life on Earth if there is no life in our soils. This is very, very important. We don't recognize this. Also, nature protection activities are often just looking on the biodiversity, on animals or specific plants in the ecosystems on the top of the soil, but not related to the underground, particularly to the soil biological and microbiological. There is, in 1 cubic meter soil under a beech forest, there are more living organisms than people on the planet. So it's really important to understand this. And this is very specific creatures that we have. They're smaller microbes, microorganisms, viruses, fungi, and of course, this is cannot be understood without the geological material and the geology that we have. And we know we have a deep biosphere that is not fueled by the aspect that I mentioned for soil-related aspect, but is fueled by geogases, and there, for instance, maybe hydrogen is playing a more important role in the process from this situation. Now, when we come back to carbon, there is about 4 to 5 times more carbon stored in the soils, and that is true throughout our planet, as in the above-ground biomass. Of course, it depends on the climate situation and on the biome, and of course, carbon sequestration, so the carbon storage depends on soil type, vegetation, and climate. The more humid, the colder, the higher it is. But it's really important to understand this. We are just writing a paper on the problem of release of CO2 out of our soils because of wrong management and of the effects of climate change. And this is significant, particularly also in Germany. And of course, it is also controlled by not just by climate change, but also by management, as I mentioned before, for waterlogging, for instance, and just a recent paper presented in Italy when we celebrated 100 years of international soil sciences showed that, of course, the management has a large impact on carbon storage, the formation of humus, but also the release of carbon in terms of CO2 or also methane. Now, to bring it again into the focus on the planetary situation, with less than 30% of the Earth's surface being terrestrial areas, 3.2% of the Earth's surface is arable land. And then you can calculate how much land per capita would be available for each and every one of us. And as the population grows, this problem becomes clearer, and therefore the relevance of soil-related discussions is now getting a focus in many aspects. Now, to understand what that means for our civilizations in the Western world, particularly, for instance, in Europe. Europe is using 60% of arable land for the supply of the way we live is consumed outside of Europe. So we use our soils here, and in addition, we use 60% outside of Europe. The US even 100%. Now you can imagine that this is not a process that will go on like this, with the population growth in different areas. So the EU uses 30 times Germany's total arable land outside its borders. So this is really, and we have good soils, we have good soils. There are no deserts, as in other areas of the world where people are now living and population is increasing. So we need to do something for the soils. So soil protection is, of course, an important aspect. We had a long discussion when we developed our soil protection law as the first soil protection law in Germany, because soils are so different and so forth. So we focused on the functions. What are the functions of soil? Of course, there should be the possibility, the potential that something can grow, plant grows, biomass, and particularly also the habitat function, that there can live something in the soil biodiversity. And then the filter control function, I showed you the question of groundwater formation, water purification. So it's not only the amount, but also the soil cleans, so to say, the water and groundwater recharge. So with this functional approach, we could then see that soil protection and how we could actually organize soil protection. And now this is in a broader perspective. The UN with the FAO in Vienna has you have in Rome you have the World Soil Charter. Even in the coming Montreal Global Biodiversity Framework now, soil health has been mentioned. We have unfortunately no SDG on soil, not on biodiversity. That might be another aspect that we have in mind. And of course, we discuss recarbonization and the effects as an ecosystem service, so that carbon should be restored in many places where we have had detrimental effects with management. And there is new approaches that we take from maybe the so-called not so developed regions now into our agricultural discussions like agroforestry or even silvipastoral approaches. And even, of course, for us human beings, soils are very important. The human body consists, I mentioned this because medical aspects will be discussed tomorrow, 60 to 70% of water, that's what it is, and the rest is carbon, oxygen, and soil. And soil, particularly, of course, the minerals, but also the minerals and living soil. So we have this soil microbiome, and we have the microbiome in our bodies, even having a clear effect on our thinking, on our psychological. Therefore, this first talk this morning is very relevant also in this context. Of course, it means via nutrition, food, via respiration, dust that we inhalate, and via skin allergies. So soil health means also human health. And it's a very important aspect when you talk bioeconomy. This is an approach where we try to replace, at least to some extent, fossil fuels, fossil carbon, so to say, with biomass. And I won't read what we just presented at the International Bioeconomy Summit in Nairobi last summer. In short, soils are essential for the survival of mankind. And therefore, this is the Landesbuch idea of the Landesbuch Soil Initiative. Bundle soil-related expertise across all fields of competence, and that includes really all fields, all of the social sciences, the medicine and so forth, and all of the integrated earth system research approaches. Provide a platform for an open inter- and transdisciplinary discourse. Transdisciplinary means also the practitioners should give their experience into this, bring into these debates and this discourse without an own agenda. So the initiative has not an own agenda, only saying that living soils are important. But what it means and how you could deal with it is open to a discourse in this initiative, where we have now about 200 people discussing this from all fields, also from industry. The engineering part plays an important role. Increase awareness on the importance of living and healthy soils, promote stewardship. So one of the aspects was what is missing, what is useful, and is development of an international and truly transdisciplinary forum for an unbiased discourse on relevant aspect, merging the expertise from science, practitioners, and decision makers. So this interaction a little bit also like SAPEA, maybe to some extent at least, what we heard this morning. Creating awareness through an aesthetic approach. When we hear these wonderful talks, it doesn't have, in many cases, it doesn't have the impact that we really do something. So maybe through the interaction with artists, with cultural approaches, we might have an aesthetic, but an evidence-based aesthetic approach. Making young people join in, and of course, getting connected with international initiatives, and that's what we are doing. So what it means, we have a lot of knowledge, but we need soil literacy and consciousness that needs to be improved, and this is what we are doing with this initiative, and thank you very much for your attendance.
Thank you very much, Reinhard, for bringing this insights on healthy soils and not so healthy soils here to this meeting. I think it's highly relevant. I think it's also clear that it is also a good thing to have you as partner in crime in the Top of Europe initiative, and we're looking forward to the next steps of what you do. We have time for one quick question. Yes, Taras.
Concerning soil policy, is it deeply embedded in the current climate and CO2 sequestration policy, or only marginally? What are relationships?
Only partial. It's not very well understood. As I mentioned, we are producing right now a paper showing that the CO2 release because of degradation of organic matter, of humus, is probably in the order of magnitude of traffic in Germany. So it would be, you would say, to reach our goals in climate neutrality, we do everything but the traffic we don't touch. That is the order of magnitude. And you can do something against, you can use the soil as a CO2 sink as for carbon storage, and also what we call long-term carbon storage. But we need different approaches for that. So there is a solution. It's not only a problem, we have solutions, but we have to act.
It seems like action is pending in this direction very clearly.
Yes,
Thank you.
Yes. And in shorter time frames than yours.
Exactly, yes.
Reinhard, is nitrogen fixation also on the agenda of this project?
Yes, this is a most important question, because we have these biological processes of nitrogen fixation, but we also have Haber-Bosch getting the nitrogen from the atmosphere and producing artificial. The problem that we have, not only in the Netherlands, but also in Germany and many other European countries, is that we have too high animal production. And for that, we get the fodder is not produced here. It's imported from Brazil or other areas in the world, as soya, for instance. And this contains high amounts of nitrogen, but the remainings remain in Europe. And therefore, Germany has a significant problem with nitrate in our groundwater, and we are not really yet in a position to really cope with this. But as such, as we don't have nitrogen generally in the parent material, it is an important process that biosphere has learned how to fix nitrogen from the atmosphere, yes.
This is also a domain where Hungary has been, for many years already, at the forefront of research.
Yeah.
I like to mention here Professor Eva Condorossi,
yes,
leading scientist on this, also chair of life sciences of Academia Europaea. And I think this is also a domain where we can make some synergy.
Nitrogen fixing species is very important, yeah.
Okay, thank you again very much. We have to move on, and